This is our first video on rotational kinematics. A radian is the angle subtended, i.e. turned through, when a point on a circle has rotated to a new location through an arc length that is equal to the circle's radius. So that's what a radian is. If we have a circle here and there's a radius, if I make that radius green in color, if I took a string and cut it the length of the radius, then I took another string and cut it to that same length and started wrapping it around, it would go to about there. And that angle right there, that's a radian. It's approximately 57.3 degrees. We know that it takes about 6 of these to go all the way around the circle because the circle is 2 pi radians. So in case you're wondering what a radian is, that's a radian right there. It's approximately 57.3 degrees. Angular position is indicated by theta. Angular displacement is delta theta. And angular position is in the unit radians, as is displacement. Angular velocity is the speed with which the angle is changing. And that's going to be measured in radians per second. And angular acceleration is the rate at which the angular velocity is changing, and that's in radians per second squared. So you can see that there are some similarities here with linear motion. Position and displacement in linear motion are both meters. Velocity in linear motion is meters per second. Acceleration is meters per second squared. So in rotational kinematics, instead of meters, we have radians. So the average angular velocity is found by taking the angular displacement and dividing by the time. If we want the instantaneous angular velocity, we take the tiny angular displacement divided by a tiny time. Those are really the same equation. This is just the average angular velocity over an incredibly short amount of time. Average angular acceleration is, we might say, a macroscopic angular acceleration. A change in velocity over a change in time that we can get our minds around. The instantaneous angular acceleration is the tiny amount of change in angular velocity divided by the tiny amount of time. And it's the instantaneous quantities that we're going to be after unless the problem directs us otherwise. So quite often, instead of instantaneous here, they'll just write alpha, or they'll just write omega. Unless we're told otherwise, we need to find the instantaneous quantities. We met 4 linear kinematics equations, and there are analogs for rotation. Instead of linear velocity, we have angular velocities. Instead of linear acceleration, we have angular. Instead of linear displacement, we have angular displacement. Essentially, all of these equations are identical, except their rotational analogs have been inserted. The time component is exactly the same. And lastly, instead of VF squared, we have omega F squared. Instead of V naught squared, we have omega naught squared. Instead of 2a delta x, we have 2 alpha delta theta. The condition that has to be satisfied to use these equations is constant acceleration. So if we're doing linear motion, it's got to be constant a. If we're doing angular motion, it's got to be constant alpha in order to use those equations. If you don't have that condition met, you cannot use those equations. Let's try an example problem here where we'll use some of these. We've got a wheel rotating initially at 2 radians per second, so that's omega naught right there. And it has a constant angular acceleration of 3 radians per second squared, so that's going to be alpha. And then there's going to be our time. So we want to find the angular velocity at the end, which is omega final. And then we want to find the angular displacement, which is delta theta. So we just need to go back to our kinematics equations, which you can rewind the video and look at those if you need to, but here's the one that is going to be most useful for this problem because we know what omega naught is. We know alpha and we know time. So I think we're going to get here 2 plus 3 times 4, 14 radians per second. In terms of angular velocity, positive and negative would typically just mean something is rotating one way versus the other. So for angular displacement, there are any number of equations we could use if we wanted to get this job done, but I'm going to go ahead and use this one. Omega naught times time plus 1/2 alpha time squared. Where possible, we always try to go back to the initial given quantities rather than use this omega final to calculate the next thing, because in case we made a mistake here, that error will propagate. So if we can, we're going to try and use the given quantities, and that's what we're doing here. So omega initial is 2, the time is 4, plus 1/2 times 3 times 4 squared. Can we do this in our head? How much does this come out to? This is 8, and this is 16, 24, 32. 32 radians. Angular displacement is in radians. Linear displacement is in meters. How many revolutions does this object make in 4 seconds? And a revolution is one time around, isn't it? One revolution. And hopefully you know that one time around is 2 pi radians, or roughly 6.28. If you'd rather type in 6.28 in the denominator, that's fine. Those radian units cancel like that. So this is going to be 32 divided by 6. It's going to be about 5, isn't it? Sometimes it's helpful to have a general idea in your head of what the answer will be before you do it. When I typed it in, I got 5.1 revolutions.